Okay. Welcome to my YouTube channel. I'll be solving the remaining past questions. So this is uh Applied Electronics 2022-2024 academic year past questions. I already solved the first 15 questions, so I'm going to continue with the next 15 questions as well. So I'll be starting from question 16. So question 16. Here, the bipolar junction transistor is a 2-layer, 3 terminals, and 2-junction semiconductor device. So what that means, we try and then look at, just have a simple sketch of a bipolar junction transistor. And we know that with this, we have what? So let's pick any of them, right? We can start with, okay, this is P and P. So if it's P and P, how many junctions do we have? You can see we have 2 junctions, right? This one and this one. And we have 3 layers, right? Or so we have what? 3 terminals, right? You can see we have 3 terminals. This is terminals here. That means we are going to have the emitter, the base. Then we have our base here. Then we have the collector. And then we have a 2-layer. And this is going to be, as you can see, we have layers. Let's say layers here is the same as the region. So you can see we have 3 regions, 2 P regions, and then 1 N region. So this is going to be false, right? Answer here is false. Okay. Now, in order for question 16, in order for bipolar junction transistor to operate properly as an amplifier, the 2 junctions must be forward biased with external device, right? You want to operate this as the 2 junctions must be forward biased with this is going to be false. As we know, when it comes to the operation of bipolar junction transistor, what we do is that the emitter base junction has to be forward biased, and then the collector base has to be reverse biased. Question 18. In between the cutoff and the saturation region along the DC load line is the amplifier region of the transistor. So this is going to be true, right? If you have our something of this nature, we have the cutoff and then our saturation in between that load line, which we call DC load line. That is going to be the region for amplification. So this is true. Now, let's look at question 19. The output characteristics of a common emitter configuration is a plot of what? Output voltage against output current at a fixed input current, i.e. So here you can see here from this one, we are being told that we are having a plot of what? Voltage, right? Output voltage against output current. But when we talk about output characteristics, we are usually talking about the output current. Is current rather against the output voltage VCE, not the other way around. So here, this is going to be false. So we have here question 19 is false. Question 20. In NPN transistor action, the base collector is forward biased to the holes in the base region and electrons in the collector region, but it's reverse biased to electron in the base region, right? This one is kind of like, I think there's a mistake with this question. Probably, I don't know whether it has been changed, but the first part is what we are interested in, right? The first part we are going to see, this is going to be true. This one here, question is true, because when you have an NPN transistor action, the base the base collector is forward bias. We know the base collector is going to be what? Reverse bias, right? That means when it comes to the holes that are going to the what? The base, right? There's going to be forward bias to the holes in the base region and the electrons in the collector region. But it's going to reverse bias to electrons in the what? The base region. So we get this to be true. Now question 21. Bipolar refers to the use of both holes and electrons as current carriers in the transistor structure. So yes, so when we are looking at holes and electrons as current carriers. So this is going to be true. Question 22. In order to obtain a high voltage amplification at the output of the transistor, the low resistance should be high. This is true. So if you want to make sure that the amplification is high, you make sure that your low resistor, meaning the resistor which is connected to the collector circuit, it should be high. Like, okay. Now let's move ahead. Question 24. A transistor is connected in common emitter configuration. The collector supply is 8 volts and then the voltage drop across a resistor of 800 ohms in the collector current is 0.5 volts. If the current gain factor, meaning alpha DC, so here we are giving alpha DC. All right, we have alpha DC to be equals to 0.96. If the current gain factor is 0.96, find the base current. So we want IB, base current. So to find this base current, we know that when it comes to base currents, we can write base current as this. Of course, we know, for example, when it comes to the emitter current, is going to be equal to the base current plus the collector current, right? Collector current. And from the question that we are giving, if the collector volt supply is 8 volts, then the voltage drop across a resistor of 800 ohms in the collector circuit is 0.5. So this resistor, which is given the 800 ohms resistor, is going to be the one that is going to be the resistance of the load, right? So that means, and we are being told that then there's a drop of 0.5 volts. So that means the voltage across the low resistor is going to be 0.5. So I can write this as VC is going to equal 0.5 volts. And we know when it comes to what? When it comes to VC, we know VC is going to equal to, meaning the RC, which is the load resistance times the what? IC. So we can make IC the subject here, and then we get 0.5 divided by 800. 0.5 divided by 800. That is going to be, IC will be equals to 6.25 10 to the power minus 4. All right. So we have this. Now that we've gotten this, we're trying to get IE, right? Because we can make the base current, the subject here, to be equals to what? The emitter current minus the collector current. So let's get, how do I find the emitter current, IE? To find emitter current, you see that we are given alpha DC. So I know alpha DC is going to be equals to, meaning the collector current over the emitter current. And then from this, we just calculated the collector current. So I can get the emitter current to be equals to, from this, it's just going to be alpha DC times what? No, it's going to rather, when we come here, we are making the emitter current the subject. So this is really going to be equals to, IC rather, over alpha DC. And this will give me, we know this to be what, 0.5 divided by 800. Okay, we know this to now be divided by 0.96. So we get this to be 6.51. Right. So we have 6.51 times 10 to the power minus 4. Now that we've done this part, we can now get our emitter, our base current to be equals to, here we can just have 6.25 minus, or is the other way around, right? The emitter, which is 6.51 minus 6.25. Remember times. We're putting 10 to the power minus 4 here. So I have 6.51 minus 6.25. That is going to give me 0.26. So from this, I'm going to get 0.26. Okay. Let me see. Okay, we have 0.5 divided by 800 divided by 0.96. Okay, so we get 0.26 times 10 to the power minus 4, and that is going to be equals to, we express this in what? We express this in micro, right? Because you can see our answers are expressed in micro. So this is now meaning we move. This will now be what? 26 times 10 to the power minus 2 times 10 to the power minus 4. So you get 26 micro amps. So the answer here becomes 26. Okay. So this is how we go about calculating the question 24. Now moving on to question 20. Question 25. Okay, let me clean some of this. So with question 25, we have in a common base connection, the emitter current is 1 milliamps. If the current is open, if the emitter circuit is open, the collector current is 50 microamps. Find the total current given alpha equals to 0.92. So if alpha is 0.92, and we are to find the total collector current. Total collector current here is going to be equals to, remember the initial current, meaning collector current equals the initial connector current, IO, plus the what? The collector current with what? With this is the collector current with the emitter being 1 milliampere, right? So to get that, how do we, so let's get the collector current to the what? The emitter current being 1 ampere. So how do we get this? Again, we can write alpha DC equals to IC over what? IE. So IC here is just going to equals to, from this, our alpha is 0.92 times the emitter current, which is 1 milli. Yeah. So that is going to be equals to, so I'll just have 0.92 times 10 to the power minus 3. So we have this as our current. Now that we've done this, so we can come and replace here, right? I have this 0.92 times 10 to the power minus 3. So we come and replace this. Now I have my initial current collector current being 50 micro. So 50 times 10 to the power minus 6 plus 0.92 times 10 to the power minus 3. So you can see that we can even make everything micro, so that we just add. Right. So if we were to make this one micro, the milli to be micro, so I can have 50 plus, rather. Let me bring here plus. So if this one is micro, remember we have 0. It's 1.92, right? This place is going to be, or you can write 0.92. 0.92, we express that as to be 10 raised to the power minus 6. So that means I have to write here 0.92 is going to be 1, 2, 3, right? So that will be 920 times 10 to the power minus 3. So we had 920. Then 9 to the power 10 to the power minus 6. So if I get 90, um, 50 plus 920, okay, times now 970 times 10 to the power minus 6. That is going to, now in milli, that is just going to 0.97 milliamps. So we get the answer here to be A, right? The answer becomes A. Okay, yeah. Now moving on to the next question. The next question, where this time, so we have this being question A. Okay. So moving on to the next question. We have find the alpha DC rating of the transistor shown in figure 1 below. Hence, determine the value of what is. Now, to find first the alpha DC, you can see here from here we are given beta, which is going to be equals, we know beta is IC over what IB. Now with this, at the same time, since we are interested in what, we are asked to find the rating of alpha DC. Mean we are asked to find alpha DC. Alpha DC is equals what? IC over what? IE. So you can see that at the same time, we know that emitter current is going to equals what? Base current plus what? Collector current. So with this, I can, since I know beta, right? You can see that here I can make IC the subject. So IC here will be equals to beta times what? IB, the base current. Now we can come and replace this IC here in this formula. I get IB plus beta IB. So that we come here and do replacement. So alpha DC here will be equals to, this is already IC, and IC we know is what? Beta and the base current. Then I have here my emitter current is what? IB plus beta plus IB. So you can see that we can factorize the base current out so that we have 1 plus beta all over IB here. We have this over. This will cancel. And then we are just going to have our alpha DC to be equals to beta, which is 4.9. Then 1 plus 4.9. So that's just going to be 4.9 divided by 50. That gives me 0.8. So we get this into 0.8. If you look at the values we already have, we have two 0.8, right? We have one A here and then another one. So now we go and get the what, and hence determine the what, the collector current. Now that we know what the alpha DC, you can just come here. Yeah, we know alpha DC, right? We still don't know the base current. So to find IC, I can come and use this formula, right? I'll come and use. Okay. Yeah. We know now IC. Yes. I know now we know alpha DC, which is what? 0.98. So 0.98. So for me to now get so I can write 0.98 to be equals to IC over what? IB, right? IB. And then based on this, we know that I is just going to IB plus this, right? So how do we find the collector current IC, right? Now to find this, again, we can come here and do some replacement, right? Do some replacement here, because if I have IE, which is equals IB plus this, and we don't know the base current, right? We don't know the base current. Here, what we can do is that we can use this idea, right? We know that the IC is always going to be 0. Okay, even here we are giving IE. Okay, we are giving IE. So we just come and use this straightforward. IC will be equals to 0.98 times 12 milli. Times 12 milli here. What do I get? We get 0.98 times 12 and 10 to the minus 3. So we get the answer here is going to be equals to IC will equals to 0. So that's just going to 11.76 milli amps. So you can see here the answer becomes D. Our answer for this is going to be D. So this, our answer becomes, okay, let me use this color, D. Now moving forward, we are now going to look at question 27. In the saturated region, the transistor acts like a poor resistor, amplifier, opens switch, close A is going to be what? B as an amplifier. If the emitter base junction is forward bias and the collector base is reverse bias, what would be the region of operation of what's for a transistor? So if the emitter base junction is forward bias and the collector base is reverse bias, right? What will be the region of operation? Cutoff region, saturated region. So here you can see that in that case, we are going to get what? The active region, right? That is just going to be collector base. So you have active region. Now the transfer of a signal in a transistor is going to be from the first one we have. The answer is going to emitter to base junction. Then question 30. All of the following are applications of transistors except, so we have A, switching current on and off, so that is correct. B, amplification of power, so the answer is going to application, because if you look at C and D, they are all what? Application of transistor. So this is the end of the second part of solution. So I'll continue in the next video. Bye-bye.